Hello everyone, welcome to the Prelab video for recrystallization. In this experiment, this is an organic one lab experiment. Um, so, uh, just to let you know, for this experiment, if you hadn't noticed or read, there's actually two different sections of the lab manual that you need to read through to be prepared for this experiment. There is the recrystallization experiment part that has the materials, introduction, the procedure, all of that stuff. But then also there is another part you need to read through, which is going to be the recrystallization theory and practice. And that should be somewhere around page 140, so towards the back of your manual. All right, and so I'm going to go over both of these fairly quickly. We're going to be investigating solvents, right? 95% ethanol. We are going to have hexane as a solvent, and we're going to have acetone as a solvent. Now we're going to be comparing all three of these as a recrystallization solvent for a variety of compounds. We have the acetanilide, the adipic acid, the acetylsalicylic acid, salicylic acid, and then there will be an unknown. All right, and the unknown isn't necessarily one of these four. You're going to notice that in the at the end of the experiment video, you're going to be using this melting point, this charts of melting points, to identify what the unknown is. All right. Now, for recrystallization, this lab report will be a full lab report. So you'll have a title page, a purpose, an introduction, safety and hazards chart. Right, I do recommend you try to draw the structures for these known compounds and the solvents. You'll also have to write up a procedure, results discussion, conclusion, and then you'll have to do the post-lab questions. All of that will be part of the lab report. Okay, and then in this procedure, right, there's as you go through, paying attention to this procedure. In a nutshell, we'll kind of talk about what's going on here, right? But you'll see in the procedure it references this recrystallization theory that you need to be prepared for. So, recrystallization theory here, right? What are we really talking about? So with recrystallization, in general, you are pretty much, the guiding principle behind recrystallization is a compound solubility. Right, and so you can either look at that compound solubility in a specific solvent, one specific solvent, or a solvent pair, a mixed solvent. But also you're going to be looking in regards to temperature. So solubility related to a specific solvent and temperature. Okay, now an ideal recrystallization solvent will have your compound of investigation should not be very soluble at room temperature. Right, so you'll still see the solid, it won't dissolve. However, at higher temperatures it will dissolve, and this would make a very good recrystallization solvent. Okay, especially if you're trying to separate a solid mixture that has more than one component to it. All right, so for instance, you're actually going to see something like that for your unknown, right? You're going to dissolve your unknown in one of those three solvents, and you're going to see a lot of the solid disappear, but some of it's going to stay behind, and that's because there are impurities in that compound mixture that won't dissolve. Okay, and so what are typically good solvents to dissolve? Well, you want to think about polarities, right? Like, as a general rule, like will dissolve like. So really what you're saying here is polar molecules will readily dissolve in a polar solvent, right? So like water, right? Water is a highly polar solvent. So polar molecules, right? And we don't really call these polar molecules, but like salts, right? They're ionically charged. They are highly soluble in water because they have exceptional polarity. Right, they're so polar, they're charged. They don't have a partial charge, they got a charge. Right, and so like dissolves like, polar molecules dissolve in polar solvents, while non-polar molecules will not dissolve in polar solvents. Okay, so something like hexane, right? That's not very soluble in water because hexane is a nonpolar molecule. All right, and so I'm going to skim through this because you really do need to kind of go through all of this kind of in your head, but there are a few criteria you want to pay attention to in this process. So for instance, when you're looking at your solvent, when you're looking at your solvent, remember like dissolves like, but also you got to remember, you don't want your compound to be very soluble at room temperature. All right, and so, but you want it to be highly soluble at high temperatures, and you want it to be soluble enough to where you can have a saturated solution. Okay, so you want it to be saturated, dissolve. You want room temperature. Very little of the material will dissolve, but under hot conditions, it will be highly soluble, and you can get a saturated compound or a saturated solution out of the mix. All right. Another criteria to kind of pay attention to here when choosing your solvent, you do not want your solvent's boiling point to be higher than the melting point of the solid you're dissolving. All right, because you are heating this, right, to increase the solubility. So if the boiling point of your solvent is higher than the melting point of your solid, you could have this this undesirable effect called oiling out, where your solid is melting in solution, and it kind of looks real ugly visually. Hopefully you never see that. Okay, and then the third criteria to pay attention to here would be solvent volatility. All right, typically you do kind of want lower boiling points for your solvents because they're a lot easier to remove that way. And so, but at the same time, you don't want it to be so volatile that when you're trying to dissolve it, it all evaporates out, all the solvent evaporates out, right? So you kind of have to balance things here. Okay, now the other side of this, something else I kind of want to talk about real quick, is because it's not really a term that we use in our it's not really a term that we use, but it kind of relates to percent yield. For the lab report, you are going to have to calculate a percent recovery. All right, and so here's the good crystals divided by impure crystals times 100. So the mass of your recrystallized solid divided by the mass of your starting material, right? So that's going to be like a mixture, something that has impurities in it, all multiplied by 100. That'll give you your percent recovery. All right, now as a kind of a general overview, just to kind of explain what you're going to be seeing here, we have what you're going to do is you're going to start with an unknown, okay, and that unknown is actually going to have, we could think of it as having two compounds in it. It's going to have compound A, the solvent you want to dissolve, and then it's going to have compound B, which is just an impurity. So what you want to see happen is that if you were to take this unknown compound, this unknown mixture, and dissolve it in a solvent at room temperature, nothing happens. You don't see anything dissolving, right? However, if you were to add hot solvent, as we see here, that's what I'm saying, we add hot solvent to the beaker, you notice how I have a lot fewer dots here, all right? And so what happened is all of the A compound dissolved. It's highly soluble in the hot solvent, but B is not soluble. So B, our impurity, kind of stays behind. And this is good because if we take this like partially dissolved mixture with B, our impurity, still being a solid, we can easily filter out B, right? So we'll have a funnel with a filter in the middle. That's what this disc is that's got crosshairs on it. When we pour that mixture in, the B solid will stay on the filter, and then our dissolved A will flow through to another container here, right? So our filtrate here. Okay, so now what we would have is a solution that has nothing but A in it. So we've separated A and B. It's got nothing but A in it. And then an easy way to isolate that would be to take that mixture, so it has dissolved A in it, and we put it with an ice bath. We cool it down. All right, and what's going to wind up happening is once we cool it down, we're going to see, oh, hey, when it's cold like that, A recrystallizes out of solution, right? It precipitates out of solution. And so then we can do yet another filtration step where we just take that, cold mixture, and we get another funnel with filter paper, and we can filter out the A. So our remaining A solid that recrystallize out would be here on the filter paper, and so that would help us get a mass of A, right? Because we would have weighed our mixture of A and B, and then we would have also weighed the filter paper, right? Done this step where we filter out the A, right? So you would have nothing but solvent in this beaker, right? So there's nothing but solvent that flows through, right? And then all the A solid would be stuck here. In an ideal world, all of the A would be there, all the A solid. Okay, and so knowing the mass of this filter paper and then weighing this filter paper with A in it, we could easily calculate a percent recovery. All right, and so that's something that you should notice as you move through the experiment. All right, at this point, you should be prepared. You're adequately prepared to move on to the pre-lab quiz.